is the interesting one. Let's spend a few minutes looking at what happens when you lift air in a way that is conditionally unstable. Well, I'm sorry, when the atmosphere or a layer of the atmosphere is conditionally unstable. So let's take an example here, where maybe down at the surface, at 1 kilometer, and 2 kilometers, and 3 kilometers, we are going to be considering the temperature. And let's take a situation where the atmosphere is conditionally unstable. In other words, the temperature, the environmental lapse rate is between the dry adiabatic lapse rate and the moist adiabatic lapse rate. Our third inequality down here. How about 8 degrees Celsius per kilometer. So let's just say the temperature at the surface was 30 degrees, and we're going to cool at 8 degrees Celsius per kilometer. So 30 minus 8 is 22. 2 kilometers up, the temperature is going to be 22 minus 8, which is 14. And 3 kilometers up, it's going to be 6 degrees Celsius. So this is the environment. We used weather balloons to measure this. And we have found that in the environment, the temperature was cooling at 8 degrees Celsius per kilometer. Let's take an air parcel down here at the surface. And let's say this air parcel has a temperature of 30 and a dew point of, let's just say 20. Let me zoom that in a little bit so you can see a little better. I apologize, I didn't bring a less thick pen than this one. Okay, we're going to lift this air parcel. Now, down here at the surface, this air is not saturated. The temperature is great. The temperature is greater than the dew point, so we're going to lift the air parcel dry adiabatically. 1 kilometer up, then the temperature has cooled by 10 degrees. 30 minus 10 is 20, and the dew point has stayed 20. Hey, we've hit a special place in the atmosphere, haven't we? We've hit a place where now the temperature and the dew point are equal. Do you remember what we called that back in the second unit? That was the lifted condensation level, the LCL. That's the base of the cloud. So, from here on up, we've made a cloud. Here's the LCL. Now, at this point, the temperature of the environment is 22. The temperature of our air parcel is 20. If we lift the air parcel, if we stop lifting it, is it going to rise or sink? It's going to sink, right? It's colder than the air around it. But, okay, maybe we gave it a little bit stronger of a push than that, and it didn't go 1 kilometer, it went 2 kilometers. Let's try that. So if we go another kilometer up, this air parcel will cool at the moist adiabatic lapse rate, because we're making a cloud. 20 degrees minus 6 degrees is 14 degrees Celsius, and our dew point, of course, is still 14 degrees Celsius. Now compare it to the temperature of the air around it. This air parcel has a temperature of 14 degrees Celsius. The environment around it has a temperature of 14 degrees Celsius. This air parcel is neutral. He's the same temperature as the air around him. And in fact, if we lifted it even 1 more kilometer up, the temperature would have decreased by another 6 degrees Celsius. 14 minus 6 is 8. And the dew point here is 8 as well. Now the temperature of the air parcel is actually warmer than the environment. Now this air parcel will rise on his own. We don't have to keep lifting him. So actually here, 2 kilometers up was an important place. Once we got the air parcel lifted up to 2 kilometers, he was the same temperature as the air around him. In fact, if we got it any higher than 2 kilometers up, he was actually warmer than the air parcel was actually warmer than the air around him, and he'll rise on his own. This is another important level in the atmosphere. In the same way that the base of the cloud was the lifted condensation level, this height in the cloud is called the level of free convection. The level of free convection. Or the LFC. The level of free convection is how high above the ground you have to lift an air parcel so that he's the same temperature as the air around him. Once you get it that high or higher, the air parcel is buoyant. He'll rise on his own. So that's the trick. On a sunshiny summer day, you look outside, and what do you see? you see all these little puffy, happy bunny clouds, right? You look outside, here's the ground. This pen sucks. Let's just get rid of it. You look outside, you see all these happy little puffy cumulus clouds. Each one of those clouds represents a situation where air rose to its lifted condensation level, but that was all the farther it got pushed. It was still colder than the environment, and it sank back down. It did not rise to the level of free convection. If we had pushed the air parcel hard enough that it had gotten as far as the level of free convection, it would have risen all the way to the top of the atmosphere. Well, it's the top of the troposphere anyway. So, on an ordinary summer day, we see all those little puffy clouds. They're all failures. Shame on them. They are someplace where the air was starting to rise. Why was the air rising in each of those little puffy clouds? Well, who knows? Maybe that was air that was a little warmer than the air around it. Maybe that was air that was over a parking lot compared to the grassy areas around the parking lot. So the air over the parking lot was a little warmer than the air over the grassy areas, and it rose. But let's face it, kind of a wussy little rise. It may have risen even as far as the lifted condensation level, made a little puffy cloud, but it didn't help that he was colder than the air around him, and at some point he sank. But if we could lift him all the way to the level of free convection, which is something you have to figure out, a meteorologist figures this out each day as to how high above the ground the level of free convection is, in the same way that we've been figuring out how high the level of the lifted condensation level was. If we can get the air to rise as high as the level of free convection, all hell breaks loose. This is what happened on Monday. All day long we had these little puffy cumulus clouds. They were worthless, but at some point a cold front came through that gave enough lift that it lifted the air to its level of free convection. Then thunderstorms happened, because then the air was warmer than the environment. We didn't have to keep pushing it. It rose on its own. So this business here about figuring out whether the air parcels will rise or not is really about figuring out if we can get air to rise as far as the level of free convection. Now, that business is largely outside the scope of this course. Largely, you would take, like the severe weather courses and so on as an atmospheric science major to learn about how we actually decide how high the level of free convection is and how we decide whether air will get that far. That's very cool. That's part of when they tell you there's a 40% chance of thunderstorms, they're figuring out the odds they think that will happen. But it's an odds thing. Okay? If the exact air parcels that rise are not quite that warm or they don't get lifted quite that high, you just don't get it. That's why sometimes they say thunderstorms are going to happen and they don't. It's because there's chance. There's all these little air parcels out there. Some are rising harder, some are rising faster, some are rising farther, some are rising less, some are rising more. But you notice that they always have their bases all at about the same height, because that's the level of the lifted condensation level. Okay. I know that this lecture today tends to saturate people. You know what I'm saying? It's a lot of arithmetic, which you were awesome at in 4th grade, but which you kind of, I helped, that wouldn't really matter. More importantly, you were always going, please tell me this has something to do with tornadoes and thunderstorms. And yes, but we had to get through this idea of stability so that we could start talking about the kinds of stability under which we'll get different kinds of thunderstorms and so on. Where will we need to have things like inversions so that we have the right stability patterns and so on to get thunderstorms or tornadoes or hurricanes or whatever, okay? So we had to make it through this to get to the sheet metal wrapped around trees part of the lectures that come the rest of the unit, okay? All right, so in that regard, then why don't we just call it an early day rather than start something else? All right. Don't forget you have that. If you want to come to that post-mortem thing this evening, it will be very helpful. It's at 5:30, not 5 as the original email message said.
Fine, yeah, it's at 5:30.
No, it's in the usual room, Hicksley 524.
And we have to go to find out our grades pretty much? We can't find out our test grade now?
You can get your test grade on Blue Line yet.
Oh, it's on Blue Line?
Your test grade, not the actual test.
Oh, I know. All right, yeah, I'd still like to know.
Yeah.
ASAP.
You've been seeing it all semester, right?
Blue Line?
Yeah.
I don't use it very well, but I think I sort of know. You
Okay.
grades,
Yes.
you
All right.
run, and then it tells you.
All right.
I will find that out.